Welcome to Chapter 10, Section 4, Inscribed Angles and Polygons. The essential questions are, how are inscribed angles related to intercepted arcs? How are the angles of an inscribed quadrilateral related to each other? What you will learn is how to use inscribed angles and how to use inscribed polygons. So some core vocabulary to start off with is an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So here we have angle B or angle ABC. So this angle ABC is an inscribed angle because its vertex is located on the circle. So if it's located on the circle, we call that an inscribed angle. Recall in the previous section, we had something called a central angle, which is an angle whose vertex is located at the center of the circle. But in this case, we have a angle who has the vertex on the circle. So this is called an inscribed angle. So then we have an arc that lies between two lines, rays or segment, is called an intercepted arc. So this angle, this inscribed angle, is creating an intercepted arc. Okay, so this is an intercepted arc. Okay, and these are going to be very related. We're going to see that in the next screen, how they are related. Okay, but first, we're going to talk about something that's called the subtend. So if the endpoints of a chord or an arc, so I'm going to draw this chord AC in the same color as the arc that it corresponds to. So if those lie on the side of an inscribed angle, then the chord or arc is said to subtend to the angle. So because this angle B, this in orange, intercepts arc AC, then arc AC subtends, or sort of maybe a different way to think about it is belongs to angle B. So AC, arc AC and segment AC subtend or belong to angle B. All right, so the measure of an inscribed angle theorem. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. So here we have, say, angle D. So the measure of this ADB, angle ADB, is going to be 1/2 of the measure of arc AB. So whatever, let's say this was 100 degrees, the arc AB is 100 degrees, then angle ABD would be 1/2 of that, which would be 50. Or it could also work the other way around, where say this angle D, let's say is 40, so then that means that that arc is 2 times that much, so 80. It works the opposite as well. So this is 80, 1/2 of that is 40. All right, so let's use that information to find the measure of the indicated pieces here. So first we want to figure out what the measure of angle T is. And angle T is this corner right here. So from our theorem, from our measure of an inscribed angle theorem, we know that this angle T is 1/2 of the arc that subtends to it. So the 1/2 of 48. 1/2 of arc RS. All right, so then the measure of angle T is 1/2 of 48, which is 24. All right, there we go. So I'm going to go ahead and take this off so you can work on the next piece. So the next thing is we want to find the measure of arc QR. So let's figure out what that piece is. So the quickest way from Q to R is this. All right, so now this is going to be a little bit tougher because what happens here is that we don't have an angle that subtends to this arc. So let's say if we had an angle here, maybe we'd be able to figure out how much that measures, but we don't know that. But what we do want to observe is we want to see what other features are located on this circle. So what I notice here is that TR is the diameter. And I know it's the diameter because it goes through the center of the circle. So because this is the diameter, I know that this arc TQR is a semicircle, which means that that's 180 degrees. So then what I need to do to find that arc QR in green is I'm going to take this 180 and I'm going to subtract this arc here, right? Because then that would give me the remaining piece, QR, which is what I need. So now I know I need to find what QT is. So let's find the measure of QT, of arc QT. So I know that the measure of arc QT, okay, is twice as big as its central angle. Okay, because remember our theorem here, it goes forward and backwards. So this one here is 2 times the center. So here I'm given the angle, so I know that the outside is going to be twice as big. So then the measure of QT, arc QT, is 100 degrees. So if this is 100, then that means that my arc QR is equal to 180 minus 100, which is 80 degrees. All right, next theorem, we have the theorem, the inscribed angles of a circle theorem. So if I have two inscribed angles of a circle that intersect the same arc, then the arcs are congruent. Then the angles are congruent, sorry. So I have here two angles. I have this one here, and I have this one here. So notice how both of those circles have the same subtending arc. So this arc AB is a part of both angles, belongs to both angles. So because they do that, then I know that the two angles here have to be the same. Okay, so that is the inscribed angles of a circle theorem. All right, so what we're going to do here is we're going to try to figure out our missing pieces here. So the first thing we're going to do is we're going to find the measure of arc RS. Okay, so let's identify arc RS. This is arc RS right here. So what we have, we know that we want to use the subtending angle. And the only one that I have labeled here is this. And I know that it belongs to that because the edges, the vertexes, the endpoints here are between the arcs. So I can use what I just did on the previous screen. I know that this angle, if I multiply it by 2, it's going to give me that. So arc RS is equal to 2 times 31. So arc RS is equal to 62 degrees. All right, so let's clear this up a little bit. And I know that this is 62 right there. So now what I'm going to do is I'm going to move on to the next piece, which is to find the measure of angle STR. So this is an angle, so let's make a corner STR. All right, so we don't have to do much math for this one because STR has the same endpoints as this angle here. So then that tells us that this angle is the same as this angle. So then I know I don't have to do much math here. I just have to say that that is also 31 degrees. We have a couple theorems now to talk about before we go on to our last example. So here we have an inscribed right triangle theorem. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. And this is important to know. If I have a right angle, which means I have a 90-degree angle, then that means that this diameter, AC, has to be the diameter. The hypotenuse has to be the diameter. Conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle has to be a right triangle. See, what I'm going to do here is I'm going to move this point B. And notice how no matter where I move point B, the triangle that is created is always going to be a right triangle. Always, no matter what. Okay, and that is the case because the hypotenuse, AC, is the diameter of the circle, and it has to work that way. In our next theorem, we have the inscribed quadrilateral theorem. So if a quadrilateral can be inscribed in a circle, so inscribed means the vertices or the points of whatever's inside are on the circle, so it's inscribed, if and only if the opposite angles are supplementary. So this is actually a little bit, I set it up pretty nicely so that we can see what that is. So the opposite angles, so angle F and angle D are opposite. We have 100 degrees and 80 degrees. If those are supplementary, then we know that this quadrilateral is inscribed. So we have 80 plus 100, that is 180. We have 74 plus 106, which is also 180. So if that is the case, if the opposite angles add up to 180, okay, then the quadrilateral lies on the circle. We know that that is the rule. All right, so we're going to apply both of these theorems that we just talked about to find the measures of each of our variables. So we're going to go ahead and start with x. So because of our first theorem, the inscribed right triangle theorem, and its converse, we have a triangle that's inscribed, and we know that AB is the diameter because it passes through the center, and its endpoints are at the edge of the circle. So then that tells us that this angle here is 90 degrees. So to solve for x, I'm going to do 2x is equal to 90, because that corner right there is equal to 90. To solve for x, I divide both sides by 2, and I get x is equal to 45. Next, let's solve for y. So we're going to use the other theorem, which is the inscribed quadrilateral theorem. If I have a quadrilateral that's inscribed, then I know that the angles that are opposite of each other have to add up to 180. So y plus 120 has to be equal to 180 because they have to be supplementary. So I'm going to subtract 120 to solve for y. So I know that angle y is equal to 60 degrees. And then we do z. Z is the same thing. We're going to do that with the opposite. I know that z plus 80 has to be supplementary or equal to 180. I solve for it by subtracting 80 to both sides, and I get z is equal to 100. All right, and then that is how you use our two theorems of inscribed polygons, either an inscribed right triangle or an inscribed quadrilateral. And that is the end of section 10.4, inscribed angles and polygons. You should know how to find the measure of an inscribed angle, how to find the measure of an intersected arc, and know what to do when there is an inscribed right triangle and when there is an inscribed quadrilateral. If you have any questions, comments, or concerns, please feel free to leave a comment in the comment section down below, and I will see you next time.